Hello everyone, welcome to the 9th video of 10 AP Physics 1 summaries. Today we'll be looking at the DC circuit unit and focusing on conceptual review. If at the end of this video you're looking for more resources, please check out my description down below for links on more concept review and application problems. If you want to target your time towards specific content areas, I will include timestamps in the comments for each topic. Let's get started. A DC circuit, or a direct current circuit, is a closed loop of flowing electrical current with electrical components like batteries, resistors, bulbs, and possibly switches. Today we are going to be focusing on the basic concepts of circuits, including Ohm's law, Kirchhoff's junction rule, and solving what I call VERP charts. Current is the movement of charge through a conductor. In direct current circuits, you can imagine current like a conveyor belt of electrons. It is measured in amperes, which is the flow of 1 coulomb of charge per second. Remember that a coulomb is 6.241 times 10 to the 18 electrons, so it is a lot of charge. Because of this, we usually work with pretty low numbers of amperes. Current can be shown as delta Q over delta T, which comes from its literal definition, but we are rarely asked to calculate I this way. Be aware that conventional current is drawn to go in the opposite direction of the actual flow of electrons. On the left, we have a series circuit. The name comes from the electrical components all being in one successive series. On the right, we have a parallel circuit, named after the parallel branches the electrical components rest on. Usually complex circuits have a mixture of these structures. When we envision current, we can think of a stream leaving one end of the battery and re-entering the battery on the other side. The same amount of water enters and leaves the battery so long as the circuit is closed. In series, current only has one path to travel, so current is constant all the way around, even across each resistor. In parallel, the stream of current splits at each junction and then comes together at the next. Imagine two rivers temporarily splitting the volume of a larger river before rejoining. This makes it so current can vary across resistors in parallel. Kirchhoff's junction rule is a fancy name for current in equals current out. It is based on the premise that charge is conserved, which allows us to say that even though the current may temporarily split into smaller segments, it will equal its initial value when it comes together. This rule allows us to simplify parallel circuits into series when solving for total values. Voltage, measured in volts, is an electric potential difference. An ideal battery has a certain voltage, sometimes called EMF for electromotive force, across its positive and negative ends. This electric potential difference can be thought of as a difference in pressure. Electrons leave the negative end of the battery, which is at a high potential, and return in through the positive end of the battery, which is at a low potential. If you're confused by that, of course you should be. This misunderstanding comes from the timeline in which electric potential and electron charge were discovered and named. It was assumed that electricity would flow from high potential to low potential from the perspective of a positive charge, and this was standardized before scientists discovered electrons' negative charge. This also caused the contradiction between the direction of conventional current and the actual direction of electron flow. Now that we know that electrons are negatively charged, our naming of positive and negative versus high potential and low potential is stuck backwards. These two symbols are used to show batteries. A battery provides voltage almost like a large water tank used to get the stream moving. It creates a natural pressure for electrons to want to flow. In series, voltage drops across each resistor. The sum of the voltage drops across the resistors equals the sum of the voltage provided by the battery. In parallel, voltage does not necessarily drop across each resistor. Rather, any number of resistors in simple parallel share the same potential difference equal to the battery's voltage. Any conductive wire uninterrupted by resistors has the same potential. So let's assign some random realistic numbers here. If we have a 3-volt battery over here, and a 3-volt battery over here. We know that any uninterrupted piece of conductive wire is going to exist at its own electric potential. So on the left we have this piece of uninterrupted wire, this piece of uninterrupted wire, this piece of uninterrupted wire, and this piece of uninterrupted wire. These are all at different electric potentials. On this side, when things are in parallel, we actually only have two different sections of wire that exist at different electric potentials. So what's happening here is that all three of these objects only have two different electric potentials, whereas this has changes across each, and that's basically where this is coming from. Just to assign some possible numbers, this is 3 volts, then this also has to be 3 volts of electric potential. Whereas over here, they have to sum up to 3. So let's say this one is 1, this is 1.5, and this is 0.5. So those are some potential, no pun intended, values for situations like these. Resistivity is a property of a material that determines its natural strength in resisting current flow. Good conductors have low resistivity, however it increases with temperature. Poor conductors, i.e. insulators, have high resistivity. Conductivity is the inverse of resistivity. See that silver has a resistivity of 1.59 times 10 to the negative 8, and a conductivity of 6.9 times 10 to the 7. These two values are inverses. A wire's internal resistance is proportional to its resistivity in length and inversely proportional to its cross-sectional area. As a student, I assumed cross-sectional area should instead be proportional to resistance because I thought, well, if the wire is wider and there's more conductive material, shouldn't the resistance be larger because it has to pass through more stuff? However, you can think instead of cross-sectional area like a hose. If you have a very narrow hose, it's going to be harder for a large volume of water to pass through. If your hose is wider and has a larger cross-sectional area, it is much easier for water to pass through. This is how cross-sectional area is inversely proportional to resistance. There's a helpful PhET simulation called Resistance in a Wire if you want to explore the relationships in this equation yourself. In series, resistance sums. The total resistance is the sum of all of the resistors in series. In parallel, the inverse of the total resistance is equal to the sum of the inverses of the resistors. The last major quantity we will calculate in circuits is power, measured in watts. Power is the rate of energy consumption. I've most often seen it come up when working with light bulbs because the brightness is based on power. This makes sense if power is energy dissipated and light is giving off light energy. Power is the product of current and voltage, so you would calculate those values first, then find power accordingly. This is the big equation for this unit, just like Newton's second in dynamics. Current is proportional to voltage and inversely proportional to resistance. Let's think this through. Current would be proportional to voltage because potential difference is like the supplier of current. EMF causes initial potential that causes the current to flow. Returning to our water analogy, the amount of current in a stream would be proportional to the water tank the stream comes from. Current would be inversely proportional to resistance because resistance is standing in the way of current. Imagine you are running and comparing resistance while running through air versus through water. There's going to be generally less movement and less current flow if there is more resistance. So here we have a simple series circuit, and we're going to be working with our usual Ohm's law and P equals IV for power. So when we are in series, we know two major things. We know that the resistance sums, and we know that the current is constant. So let's start by finding the total resistance, which is going to help us find the current that's constant. So our sum equals the sum of R1, R2, and R3, which equals 10 plus 25 plus 5, or 40 ohms. With this value, the total resistance, we can find the current. So we have I equals the voltage, which is 10 volts given by the battery up here, 10 volts over 40 ohms. And with that, we can find that the current across all parts of this circuit is equal to 0.25 amps. So now that we have the current, we can go through each resistor and find the voltage drop. So if we have current 0.25, and this is again applying Ohm's law, equals the voltage of this specific one, which we don't know, then we have the resistance of R1 is 10 ohms. And we can use this to find that the voltage drop across R1 is equal to 2.5. Doing the same process for our, this was supposed to be a 2, we have I, which equals 0.25, and then this equals V over R. We don't know what V is, it's another question mark, over the resistance, which is 25 ohms. And then we get, doing the same thing, constant current, so 0.25 amps equals question mark and 4V, and then over 5 ohms is equal to 1.25. So here we have the total voltage drops, and we can check that these are correct by summing them up and seeing if they equal 10, because we know in series all of the sums of the voltage drops should equal the voltage across the battery. And the sum of V1 plus V2 plus V3 does equal 10, so we should be good to go. Now for finding power, what we want to do is just use P equals IV. So we have the current of 0.25 and the voltage of 2.5, 6.25, and 1.25, and we can find by multiplying 0.25 by each of these their respective powers. So here we have our answers. It's a little bit of a lengthy process, but we are going to come up on a way to make this a lot simpler for ourselves. So now for another simple example, but this time working in parallel. So we're going to start again just writing Ohm's law up top and P equals IV for reference. We have a 10 ohm resistor, a 25 ohm resistor, and a 10 volt battery. So when we are working in parallel, some of the key ideas here are that the voltage drop is the same across all resistors, and that it's equal to the voltage of the battery. We also know that the current across the branches sums to the total current. So let's start by finding the total resistance here. We have 1 over R equivalent equals 1 over R1 plus 1 over R2. So then we have 1 over R equivalent equals 1 over 10 plus 1 over 25. So then we get an R equivalent of approximately 7.14. Once we have this total resistance and we know that we have a voltage that is constant across the whole thing, we can find the total current, which should equal the voltage over the total resistance. And we get an answer of about 1.4 amps. So what we're going to do with this total current is we're going to use it to check our values that we get here, because we know that we should find the current in this plus the current in this equals this value. So now let's start working with our individual resistors, R1 and R2. So we know that I is equal to the voltage across this, which we know is 10, over the resistance, which is given also to be 10 for R1. So we get 1 in the top branch. Then for R2, we have I equals the voltage, which is again constant, and then the voltage, or the resistance, sorry, in R2 is 25. So we get 0.4. And we can find that these are equal to 1.4. So that checks out. Now let's just follow the same basic procedure for power, multiplying I times V. And for this one, we will get 10 watts, and for P2, we will find 4 watts. So again, a pretty basic procedure, but it can get a little bit messy. Luckily, there are strategies that make solving circuits much easier, so let's take a look at those. To avoid the hassle of manually doing out the equations and trying to stay organized while solving circuits, there are a couple of steps you can take to make your life easier. Remember to first draw simplified versions of the circuit, especially to consolidate resistors. Then work backwards from the simplified version to solve the components of the complex circuit. Secondly, use a VERP chart. This is a chart that organizes voltage, current, resistance, and power and uses Ohm's law to solve. Here is an example. So we have our chart, we have our circuit right here, and we have our equations up top. First, what we're going to do is simplify the circuits in 2 steps. So first we're going to use the equation 1 over R equivalent equals 1 over R1 plus 1 over R2 to consolidate these parallel resistors into a set of series resistors. Then what we're going to do is sum these series resistor to find a total resistor. Using this simplified circuit, we're going to solve for the totals of V, I, R, and P using Ohm's law. We know that voltage equals 24 volts and resistance equals 199 ohms. So we can find current using I equals VR. From here, find power using P equals IV, and we get these values. We are filling them into the end of our table because they are the totals, so we're going to be checking other values against them. Now let's move backwards. We'll start by listing all of the resistors in the most complex version of the circuit, followed by their equivalent resistors. So taking the 100, 250, followed by the 71.4 that replaces it. And then I'm going to highlight the equivalent resistors so that we can check that their sum is equal to the total resistor. If we focus on this middle circuit diagram, we can see the resistors are in series. That means that current is constant throughout the entire circuit, so we can fill in the total current for each of these resistors too. Then, after another application of Ohm's law, we find voltage across each of these resistors. Notice that the sum of the new voltages equals the sum of the total voltage. Now that we solve V, I, and R for the medium level circuit, let's finish finding the values for the most complex version. We can see that the 100 and 250 are in parallel and that they make the 71.4 ohm resistor. Because the 100 and 250 are in parallel, we know that they have equal potential difference across them. Recall that any conductive wire uninterrupted by resistor has the same potential level, and they are connected on either end by one continuous wire, so this holds true for them. We can fill in that they have the same voltage, i.e. potential difference, as their simplified version. The same logic applies to the set of parallel resistors below, so basically what we're doing, we're taking the potential difference of this and assigning it to these, because they have to have equal since they are in parallel. We have now filled in all of the voltage column and all of the resistor column, so we can use Ohm's law to solve for the remaining current column. Once we do this, we can use P equals IV to solve for power. Notice that the highlighted power values sum to the total power, and the non-highlighted power values from the most complex version sum to the highlighted. This may seem a little bit complicated, but once you get the hang of it, I promise you will realize how valuable of a tool it is, even just considering the organizational aspect. The general method is that we simplify the circuit diagram, and that we then work backwards to solve. Okay, just one more video to go. In my next video, we'll be going through content area 10, mechanical waves and sound. Thank you so much for watching, and be sure to check out the description down below for more resources and more about me. I'll catch you in the next one for more AP Physics 1 content.